Hello everyone, welcome to the course on biostatistics and design of experiments. We will talk little bit more on chi-square test, and later on we will take up another new distribution called the Weibull distribution. As I said, chi-square test looks at goodness of fit. It can see whether there is an association between a group and another group. So it is quite a very useful type of test. So for example, if I have some observed data and I expect something else, then chi-square test can be used to determine whether the observed data is very different from the expected data. Okay, so here the null hypothesis will be observed will be same as expected, and the alternate hypothesis will be observed is not equal to expected. So the test statistics will be observed minus expected square divided by expected, you sum it up over all the data points, and that will give you your chi-square. Then you compare this chi-square with the table chi-square for k minus 1 degrees of freedom, and as usual if the test statistics is less than table, there is no reason for you to reject the null hypothesis. If the test statistics is greater, then I need to reject the null hypothesis and accept the alternate hypothesis. Of course, there is something called edge correction, especially it is very valid when you are doing a 2 by 2 type of contingency table. So because when you do a 2 by 2, it is you are converting a continuous distribution, chi-square is a continuous distribution, into sort of an integer, almost like binomial, yes, no, live, dead and so on. So in order to take care of these discontinuity, especially when you are handling 2 by 2 contingency table, there is something called the edge correction that has to be done. Some softwares might not do that actually. So what does the edge correction do? Expected minus outcome, you take the absolute value and subtract from minus 0.5 from that, that means subtract 0.5 from there. Okay. So you need to subtract 0.5 from the absolute value. Okay. Sometimes you will get expected minus observed negative, but that does not mean you will add another 0.5 negative to that. Then if the subtraction reduces to below 0, then you just equate it to 0. Okay. So these points you need to remember, especially when you are using edge correction. Now I also mentioned there is a table for chi-square, just like a table for f test, t test, z test and so on. So in that table, as you can see here, here you have the degrees of freedom, here you have the probability, here you see the two sided and one sided probability. Okay, so generally one sided 95% is here. So this gives you the lower boundary and this gives you the upper boundary. So generally 95% chi-square we may end up using this particular column. Okay, let us look at one more problem. I am trying to do as many problems as possible so that you gain a lot of confidence in organizing and solving this type of problems. Okay. Okay, so we have 5 different antiseptic formulations. Okay. So 5 different antiseptic formulations are prepared and they are given to rural medical centers, and the feedback on their acceptability was received. So accepted, not accepted. So you get feedback. So it's the beauty of it is it need not be, the total need not be the same. As you can see here, total need not be the same. You may get different sets of feedback. Some rural hospitals may give you feedback, some might not give. So it does not matter. So we have 5 formulations. Accepted of for A we get 14, not accepted we get 22 and so on actually. So we know this is the observed data. So obviously we need to do the expected data, and then we do the chi-square test statistics calculation. Okay, let us go forward. So formulation A, B, C, D, E accepted. Okay, this is the observed. Okay, I have just copied the whole thing here, not accepted. So if you add up all these accepted you get 76, if you add up all these not accepted you get 105, if you go across these rows we get 36, this gives you 38, this gives you 36. this gives you 37, this gives you 34. So, the grand total is 181. So, if I want to calculate what is the expected here, I taught you last time, it is quite simple, 76 divided by 181 multiplied by 36. Okay. So, that will give you 15.12. If you want to know what about this, what is the expected for formulation B in accepted, 76 divided by 181 multiplied by 38. Okay. So, here for C we do 76 divided by 181 into 36. Okay. And then for D we say 76 divided by 181 multiplied by 37, and for E 76 divided by 181 multiplied by 34. So, if I want to go here, what do? I say 105 divided by 181 into 36, 105 divided by 181 into 38, 105 divided by 181 multiplied by 36, 105 divided by 181 into 37, 105 divided by 181 into 34. Okay. And finally, they will all add up row wise, column wise, grand total, just to cross check whether your calculations are okay. So, we end up having these are the observed and these are the expected. Okay. So, these are the observed, these are the expected. So, we start doing the test statistics estimation. So, it is quite simple. So, what do? Expected minus observed. Okay. Expected minus the observed, do you understand, divided by expected, and the bottom it will come, right. So, it can be observed minus expected or expected minus observed, because we are anyway going to square it, but the bottom will be expected. So, these are the values. We are having how many, 5 here and another 5 here. So, totally 10, okay, 5 totally 10, and then we do the squaring, we do the squaring divided by E. So, summation of E minus O square divided by E. Okay. So, it comes out to be 6.16, comes out to be 6.16. So, we have how many degrees of freedom? We have 5 antiseptics. So, obviously, we have 4 degrees of freedom, P is equal to 0.5, 4 degrees of freedom. So, we go down here, we say 9.49. So, obviously, the test statistics is less than the table. So, cannot reject null hypothesis. So, we cannot conclude that there is a real difference between each of these formulations. Okay. So, we have to as of now say that all the 5 formulations are the same. So, we cannot conclude because our test statistics is less than the table value. Okay, we can do the same problem using Excel also. Okay. So, we can do the same problem using Excel also. So, let me show you how to do it in the Excel. Okay. So, we do the Excel. So, copy these 5 items, we put them together, and then we copy these 5 we copy these 5 items and put them together. So, that is the observed, and then we copy these 5 items and put them here, and then we copy these 5 items, put them here. So, this gives you the expected, this gives the observed. So, what do? Chi test. So, we have to put the actual divided by expected. So, expected is this is the actual. So, we just do it comma comma. So, the p value comes out to be 0.723. Okay. So, there is no reason for you to reject the null hypothesis. Okay. So, if you use the graph pad cannot do a very detailed calculation. As I showed you originally, graph pad can estimate the p value from the chi-square, or from the p value it can give you a chi-square. That is all it can do. It cannot really process in detail like Excel is able to do. Okay. So, what do we do for a 95%? Okay, for a 95% and 0.5, how many degrees of freedom we have? If you look at our problem, we have 5 formulations. So, obviously, we have 4 degrees of freedom. So, for 4 degrees of freedom it will give you what is the probability. Okay. So, it will give you 9.4877, and in fact as I originally told you that is exactly like your table. Okay. So, 9 this one. Okay. So, the graph pad just gives you the chi-square value given your probability of 0.05. So, Excel can the chi-test command in Excel can do this problem, and it can give you a probability, and so we can conclude that there is no reason for us to reject the null hypothesis. So, that means we can conclude, okay, so we cannot conclude that there is a real difference between each of these formulations. Okay, we cannot conclude that there is a difference. So, obviously that is because we have to accept the null hypothesis. Okay, now I want to leave it as a homework. Another problem here, I think you people should try to work it out. So, here we have 3 situations: no complaint, medical complaints, medical complaint, and non-medical complaint. So, no complaint, medical complaint, non-medical complaint, and these are the total of people who stayed back, and these are the people who left the medical clinic. So, we want to, they are asking you analyze this data to see if there is a relationship between complaint, okay, and non-medical, that is medical and non-medical, and then leaving the clinic or not leaving the clinic. So, it is quite simple, but only thing is you need to make 2 different 2 by 2 type of table. One is we can look at only this medical complaint, non-medical complaint. Other one is we can look at no complaint versus complaint. Okay. Okay. So, we can do that both actually, no complaint versus total of these complaint, or medical complaint versus non-medical complaint. So, I am leaving this as a homework for you people to look at actually. Okay. Now let us change gears, we will look at another distribution. So, this is called the Weibull distribution. Weibull distribution is used quite a lot in reliability analysis. Okay. So, imagine we have a part, what is the time taken for the part to fail, time to failure. Okay. That is very important, because nowadays a lot of biomaterials are implanted into the body. One needs to know how long it will last. Will it last for hours, weeks, months, years? What is the probability associated with that? Okay. So, it is extremely useful, the Weibull distribution, used in medical research, quality control. You are making millions of artificial valve. What is the failure rate of these artificial valve? How much percentage of this fails in say 2 months, how much percentage of this fails in 1 year, and so on actually. Finance, of course, is quite a lot used. It tells you how reliable a particular share market is, and so on actually. Climate, what will be the reliability of the climate. So, basically it is looking at time to failure data, such as the probability that a part fails after 1, 2 or more years. Like I said, it is extremely useful in biomaterial research when you are making various types of biomaterials like artificial valves or tendons or some of the knee joints. One is interested to know the reliability of this material. Will it last for 10 years? Given a 95% probability, will it last for lifelong, and so on actually. Okay. So, the Weibull distribution plays a very important role in identifying such situations. It has got 3 parameters: beta, it is called shape; scale is called eta, okay, and gamma, threshold parameter or location actually. So, this is generally called a 3 parameter Weibull distribution, okay, shape, scale, and threshold or location, it is said. So, the probability density function for a Weibull distribution looks like this: beta divided by eta, okay, t minus gamma divided by eta, beta minus 1, e power minus t gamma divided by eta beta. So, you do not have to get scared about it, but the softwares can determine these, no, there are softwares which can give this. So, ft is always greater than 0 as t becomes 0, okay, and gamma that is the threshold parameter or location lies between minus infinity to infinity, whereas beta and eta are always greater than 0. Okay, understand. So, this is how the distribution function looks like. Okay. So, generally the threshold parameter is set to 0, that means the gamma is set to 0, okay, then you end up having a 2 parameter Weibull distribution, you understand. So, so it is here beta and eta will always be greater than 0. So, non-negative variables beta and eta. So, it is easy to look at, no, t is your time and the probability. So, we have 2 different parameters, beta indicates shape and eta indicates scale. Okay. Okay. So, how does it look like? Let us look at the shape parameter beta and let us look at the other parameter, the scale parameter eta later. Okay, shape parameter, if beta is 3, it is also, beta is also known as the Weibull slope, because you can see here, you know, it is a multiplication number. So, obviously it is called a slope actually. Beta is equal to the slope of the line in a probability plot. So, when beta is equal to 3, it looks like a normal distribution, you see this, and beta between 2 and 4 still approximately normal. So, beta lower, now you can see this, it is a right skewed curve, and beta is greater than 10. So, you get a left skewed curve, that means data is missing on the left, here you have the data missing on the right. So, by varying the beta we can arrive at skewed distributions, and between 2 to 4 value of beta you end up having approximately a normal distribution. As you can see here, when beta is 3, it is approximately normal distribution. Okay. So, let us look at the probability plot. Here we have the time here, and then we have the unreliability here, that is the ft here, okay, capital Ft as against small ft, please note. So, beta is the slope, okay, beta 0.05, beta is equal to 1, beta is equal to 3 and so on actually, and generally around 3.5 it is a normal distribution actually. Beta is equal to 1 is a exponential distribution, constant failure rate, that means parts will fail in a very constant manner, there is no relationship with respect to time at all, it will keep on failing regularly. Beta less than 1, decreasing failure rate, okay, or decreasing hazard rate. So, as time goes up the failure rate goes down. Beta greater than 1, increasing failure rate. No, some of these for example electronic components, as time goes up the percentage of failure will also go up actually. So, beta greater than 1. So, beta less than 1 we will say it is an exponential distribution, okay. Beta about 3.5 is a normal distribution, beta greater than 1 increasing failure rate, beta less than 1 decreasing failure rate actually, okay. So, let us look at the scale parameter eta. So, we looked at beta, okay, beta is the shape parameter, okay, like this actually, it is also an indication of the failure rate. So, if beta is greater than 1 it is increasing failure rate, as time goes up the percentage of failure rate also increases, okay. Many parts may follow this. When beta less than 1 it is a decreasing failure rate, that means as time keeps increasing, okay, the failure rate goes down, that is beta less than 1. Okay. The next one is called the scale parameter eta. It gives you characteristic life, the scale or characteristic life, and it is the 63.2 percentile of the data. Now, this eta has the same unit as time, that is hours, miles, cycles, actuations and so on actually. So, when I change eta, it has the same effect on the distribution as change of the abscissa, okay. So, it is on the, like the x axis. It defines the Weibulls curve's relation to the threshold, which is analogous to the way the mean defines the position of a normal curve, you understand. So, if I have a mean of 20, so the normal distribution will get shifted more and then 20. If I have the mean of say 5, then normal distribution will be closer to 5. You understand? So it gets moved this way, that way, and that is called the position of the normal curve. So eta is indication of that. So a scale of 10 indicates that 63.2% of the equipment will fail in the first 10 hours after the threshold time. Okay. So when I say eta is equal to 10, it is extremely useful because we can say 63.2% of the equipment will fail in the first 10 hours after the threshold time. Okay. So ideally we would like to have larger eta. Increasing the value of eta with beta constant has the effect of stretching out the probability distribution function, you understand. So ideally I should have a very large eta, so that the failure can be pushed more and more to larger times, you understand. So both are very logical. The first one is called the shape. It tells you how it looks like, whether it is normal, whether skewed. So if it is less than 1, it is a decreasing failure, greater than 1 it is increasing failure rate. Okay. Beta is equal to 1 constant failure rate. So irrespective of time, failure happens regularly and so on actually. Whereas eta is like stretching your moving your curve to the right. Larger the eta, longer is it for failure. So if eta is equal to 10, it indicates 63.2% of the equipment will fail in the first 10 hours after the threshold time. Okay. So if eta is increased while beta and gamma are kept constant, the distribution gets stretched out to the right. Okay, as you can see in this picture, right. So we have beta is equal to 3, eta is equal to 50, that means 63.2% of the equipment will fail in the 50 time units. So whereas if I put eta is equal to 100, so the 63.2 will fail in 100 time units. If the time is hours, so in 100 hours 63.2% of the material will fail. If eta is equal to 200, then 63.2% of the material will fail in the within 200 hours. Okay. So if eta is decreased while beta and gamma constant, the distribution gets pushed towards the left and its height increases, whereas if eta is increased, the height will decrease, but the graph will get pushed more and more to the right. Okay. Do you understand? So it plays a very important role. Okay. So the threshold parameter gamma, we generally said we do not have to bother about it. So threshold parameter generally indicates the shift of the entire distribution to the right or to the left. Okay. So if it is 0, we can say the graph will start from the origin. If I give some value, the whole graph gets shifted here, as you can see in this picture. So a negative threshold shifts the distribution to the left of 0, whereas a positive threshold shifts it to the right. So all data will be greater than that threshold. Okay. So a 2 parameter Weibull distribution like say 400, exactly same as a 3 parameter Weibull distribution 400 into 30, except the whole thing has been shifted by 30 units to the right of 0 actually. So if this is 10, 20, 30, a 2 parameter 400 is same as a 3 parameter 430, but only thing is the graph will look like this. Weibull distribution is an alternate to the normal distribution in the case of skewed data. So if your data is skewed, so we can use Weibull distribution. The exponential distribution is a special case of Weibull. So it can be used, frequently used to study the scattering of radiation or wind speed, because I said if beta is equal to 1, constant failure rate. So irrespective of time, constantly parts fail actually. Okay. So wind speed it follows maybe the exponential distribution. Now gamma also has the same units as t, because it is shifting the graph to the right or to the left, so it should have the time unit. So gamma and eta will have the units of time. understand. Okay. So, we will continue further on this Weibull distribution in the next class. Thank you very much.